You can start each other.
I was going to do it, but you guys can
Oh,
go ahead.
yeah.
Oh, you can actually do that.
Go for it.
Alright, so our next group will be presenting Steelbridge Team 2013, and they are James Beal, Silva Garcia, Ren Kimura, and Scott Nora.
Oh, perfect timing. So welcome. We are the 2013 Steelbridge team. My name is Sylvia Garcia.
And Scott Nowak. James Beal.
And running tomorrow.
We will begin the presentation by giving the reasons why we chose this project. We will then talk about the competition details. And then that'll set us up to really go into our approach and why it is unique. Then we will talk about the construction of our bridge and the build team selection. Finally, we'll talk about the competition day and our results. At the end, there'll be time for questions. So every year, the American Society of Civil Engineers has a national competition for steel bridge. In order to qualify, you need to be in the top schools of your region. We belong to the Mid-Pacific region with 11 schools, including Berkeley, San Jose State, and even a school from China. The unique thing about this year is that we co-hosted the event with San Jose State. It was hosted on April 19th and 20th. And usually it's in March, but it actually worked out for us. March tends to be our finals week, so it got pushed back after spring break for us. And there's other competition aside from Steel Bridge. There's Concrete Canoe, mini games, and Geotech Challenge. This past year, Santa Clara celebrated 100 years of engineering, and being a part of the Mid-Pacific Conference has been a part of that 100-year history for the Civil Engineering Department. Unfortunately, the last few years we have not performed at the level that our institution really is at, and so that was the first reason for picking this project. We wanted to change the reputation that the competition had for our school, and also regain that reputation within industry. The second reason we chose this project, we wanted to have a practical project that had both design and construction, the way that the project is set up, because we have such an early deliverable of the construction project, we felt that the design build approach would be the best. Not only is it increasingly popular in industry, but it allows us in fall, when we get the rules, to be able to sit down, have a design partially completed when we can start construction, and then other aspects of the design can continue in an iterative process until the competition. And the link to construction goes beyond just design build. Just like an engineer would sit down with building codes to design something, we're given a 40-page rule book by which we have to build our bridge. This year's bridge is 16.5 feet long with a 3.5-foot cantilever, and every single member has to fit within this box that is 4 inches by 6 inches by 36 inches. Now Scotty will talk about the competition details.
All right, thank you, Sylvia. So the goal of the competition is really to represent a steel bridge, a real-life size project in a scaled model version. So like all the other elements in the project, the members, tools, fasteners, construction site are all scaled. So as you can see here, this is the site layout for the actual competition, a 66 by 20 foot layout, with members, tools, fasteners having specific areas in which they're supposed to be. The bridge gets built over a 12-foot river with a 4-foot coffer dam in the center. And during the competition, members are brought over one by one to the constructed area, with builders being able to stand on either side of the river or actually in the coffer dam. So once the bridge is built, you go into structural loading, first with lateral loading. A 75-pound preload is located on the center of the bridge to really stabilize the bridge during loading. Once the bridge is deemed stable, there are two 50-pound lateral poles pulled at the center of the bridge and at the cantilevered section. These tests help to determine whether the bridge is stable for vertical loading, whether there will be any torsional, lateral torsional effects, etc. So once this is passed, this is really a pass-fail type scenario for loading. And so once you do pass it, though, you go into vertical loading, which we did pass. And they load the bridge with 2,500 pounds. First being the 1,500 pounds located 7 feet away from the end of the main of the bridge. This was our most critical loading case. This was before the other 1,000 pounds was loaded on, but this created our maximum moment throughout the bridge. This is what we designed all our elements for our bridge for. So this was our big case. Once we passed, we were relieved and put another 1,000 pounds on the end of the cantilever section, induced a little more shear, but kind of reversed the moment, so we were pretty safe with what effects would be occurring in the bridge. During the competition, they measured deflection in 2 cases on the cantilever section and 1 in the main span. And so what does this all mean? How do you quantify all this data? So it gets all worked into 2 equations, construction cost and structural efficiency. During the competition, you're put against the clock for build time, with how many builders you can build with. Also, it goes into how you design your bridge. So the total weight of your bridge, how heavy it was, and also what I just talked about, the aggregate deflection of where they measure the vertical loading. That sums to how really well designed your bridge is. So all these factors, they all get factored into equations, with build time being in minutes and seconds, total weight being in pounds, and aggregate deflection being in inches. You had to factor it some way. So they came up with an overall performance equation, which came down to an overall cost, which is in millions of dollars. Not really our actual cost of our bridge, but it helped you to discern which bridge did better than the other.
We only wish we had that kind of budget.
Yeah. And so now knowing all of this, what do we do? So Ren's going to talk about our team approach and how we designed our bridge.
Thank you, Scotty. So as Sylvia mentioned, our past performances in this competition really does not reflect the quality of civil engineers we have here at Santa Clara. So that was sort of our approach this year. We wanted to be competitive not only this year, but for many years to come. So we wanted to develop a bridge that future teams could learn from in our designs and ideas, and really provide a platform which can help them steadily improve each and every year. So in the past, the Steel Bridge team has been a 2-person project, but this year we felt that with 4 people, it would allow us to have firm control over the many components that surround this project. So we were actually able to divide this project into 4 equal parts that really played into each individual member's strengths. Okay, so sort of the underlying theme for our project was to be very aggressive and very proactive. In the past, Steel Bridge teams have been very internal in regards to seeking out funding and design ideas. So we wanted to kind of extend beyond the campus and really seek knowledge, funding, and expertise from professional construction industries. Brian Maple here from BMA was a huge supporter of our team. So in order to raise over $12,000, this process did not only begin in the fall quarter of our senior year, but actually in the spring and summer of our junior year. We felt the type of steel that our bridge is made of, as well as how well it's constructed, really plays an integral role in how well our bridge performs in the actual competition. So funding kind of allowed us to purchase that high quality steel and really make us competitive in the competition. Where to begin? We had no idea, the 4 of us had no expertise or experience designing a bridge, so we actually started off as 2 separate teams, Scotty and myself, Sylvia and Jay. We designed 2 completely different designs, which actually worked out perfectly. It allowed us to bounce ideas off of one another. So we had a preliminary design competition. We then combined into one big team. And after further testing and development, we were able to pick and choose what we liked about each bridge, the strengths, and incorporate those individual bridges into one final design that Scotty will talk about in the next slide. The next step was to select the build team that will compete in the actual competition on April 20th.
So what Ren just talked about, we had a preliminary design competition. So we had 2 different bridges, 2 completely different styles and approaches of designing the bridge. So the first bridge was a very idealized structure, not really meant to really actualize a bridge. The triangular girder section was actually designed and fabricated by the team, which Jay shows here. Tons of little diagonal elements involved. The second design was designed after the 2013 specifications and rules, really to create the smallest footprint dimensionally by the rule standards. And then finally, after consideration from outside sources and internally, we designed a final bridge. Utilizing our tripod section, our triangular section, as our primary girder, and then really taking the dimensional aspects of the second design. Just some pictures. And now Jay and I will talk about the finite elements, what went into our bridge. So first, we're going to talk about the primary girder. So why call it the primary girder? Primary girder takes the primary bending loads due to lateral loading. And as you can see here, we actually simplified the design. Here is the new primary girder. Very simplified, used a lot of plates instead of diagonals for simple fabrication. So why we designed it this way, the two top tubes of the girder section helps to support it laterally, those lateral torsional effects that we were talking about. And then the bottom tube helps to drive the centroid of the section down to really stiffen the member up.
So just because we had a relatively stiff primary section, it doesn't really matter if the section is stiff if the connection isn't stiff, because the section might not necessarily bend, but you'll accumulate slip along each one of the connections and you'll still have poor performance. So we needed a moment-resistant connection to connect the primary elements. So that's what drove us to come up with this style connection. It's relatively simple. It's just 2 bolts in single shear. We wanted the depth of the connection to be relatively large to help drive the eccentricity of the bolts out and minimize the amount of force in each bolt to resist moment.
So even though we created a very stiff primary girder section, we were still very worried about deflection. Just during testing, we can't really tell what effects might happen. So we designed a secondary girder system, help stiffen our bridge. So driving material away from the centroid, driving that centroid down, and actually created a stiffer bridge by a factor of 16, which was really nice.
So Scotty was talking about the secondary system driving the centroid deeper in the section. And what that really means, the depth from the centroid down to this secondary system, as the bridge starts to bend, the secondary system develops a tremendous amount of tension. And that's really all we designed that secondary connection to withstand. So it's just a single bolt in single shear, and it's meant to very, very close clearance, and it's just meant to resist slipping when the secondary system goes into tension. So then we also had to connect the secondary system to the primary system. So the secondary system is just a simple truss. When the main span bends, you get tension and compression forces in each one of these little diagonals, and it creates a net resultant shear across the connection to the primary system. So the connection was simply designed to transfer that shear into the primary section. That's also the reason for the shear plates on the primary section in both locations. So relatively simple, just a little trapezoid plate with weld on both sides and welds very strong in shear.
So designing all these connections, all these members, we were really happy with our performance, our intended performance of our bridge. But we wanted to do one more thing. So for the complete girder system, we actually staggered the primary and secondary members so that we don't get any, what Jay talked about, deflection from the connection pieces. So we didn't want any accumulated deflection. So we have, wherever there's a secondary to secondary connection, the primary girder is continuous, and wherever there is a primary to primary connection, the secondary is continuous, eliminating that accumulated deflection.
So just because we had a stiff girder system, we needed to continue the load path into the columns and then down into the ground. So once again, we needed a moment-resistant connection, and these connections had to resist a decent amount of load. So we went with a simple T that gets welded into the primary girder, and then a channel that gets welded onto the side of the column. And then 4 bolts, we had to drive, once again, the depth of that plate up to help increase the eccentricity of the bolts and prevent bearing failure at each one of the bolt locations. So as you just saw, there's only 4 kinds of connections in the entire bridge. They're all made with 4130 aircraft grade chromoly steel, and they all use high strength bolts in single shear. So really simple design, something that we were able to have a preliminary design come up with a sample connection, and then go to the lab, test, and verify our performance. And then we would iterate to eliminate any behaviors that we didn't like. So this is some of the testing that we did. This is an example secondary connection. So this is to resist the tension that's created between secondary members when the bridge goes into bending. So when you punch a hole in something, you reduce the amount of area available to resist that tension load. So we increase the area away from the bolt hole with the idea of compensating for the reduction in area. The problem that we have, when this is pulled, the load spread, the angle is so shallow that you actually don't engage any of the material out here. It doesn't see any stress before you have a deformation and rupture at the end of the plate here. So based upon that, we eliminated the extra area, and this is very similar to our final connection that's on the bridge. This is a girder column and primary connection testing. Really the important thing here that we noticed, going into this primary connection, the tube that goes into it, this guy, is relatively flexible, and this plate is relatively stiff. And the huge change in stiffness that you have in a very short amount of distance created a stress concentration, and we got premature fracture in the bottom part of this tube. So we thought that just by eliminating that flange, that was going to reduce that huge stiffness change that we were seeing and eliminate the stress concentration. We'll talk about how that worked out in a little bit. So even though we had a design that we were really happy with, we had to build the bridge, and we had to make it perform like our hand and computer analysis said it would. So we used the Maker Lab on campus. They have a new laser cutter that's capable of making cuts accurate to 3/10,000ths of an inch. We laser cut 1/8" birch ply and made all of these jigs. And the jigs are really simple. You just drop each plate and connection piece in place and then send it off to the weld shop for fabrication. So building the bridge, since Ren said we had never done this before, took us about 5 weeks and 500 hours just to take raw steel stock and cut it and make it the size that we needed. And we learned a lot about the challenges of doing things in certain orders. So making little cuts after something was welded, and just how incredibly time consuming that kind of thing can be. So this is actually the lateral system being installed. This is a little wood hanger that we cut on the laser cutter. This system was installed after the whole bridge was bolted together. So we had the bridge sitting in the quad, we hung the lateral system on it, loaded it in a U-Haul, and dropped it off at the weld shop for them to make their final welds to attach these little tabs. So we got it back 2 weeks to practice assembly before our competition, and we were really excited to compete.
So after the construction of the bridge was completed, we then needed to select the build team that would compete in the actual competition. So our team reached out to civil engineers and selected 4 underclassmen, 2 juniors and 2 sophomores. This helped us to not only achieve the teamwork aspect, but also helped us to establish the continuity we wanted to provide for future teams, which Sylvia will touch upon at the end of the presentation. So the way our bridge was designed, we felt that the most effective way to construct our bridge during the competition was to utilize the maximum of 6 builders. 2 people at the cantilever end, 2 people in the cofferdam, and 2 runners. So after many trials and many practices, we were able to put together what we felt the team that would give us the best chance to win the competition.
So we had our bridge, we had our build team, but there was one more problem. Even though we got rid of that second flange on the primary connection plate, we still were seeing premature fracture in this bottom tube. So we decided we needed to add some gusset plates only days before the competition. The gusset plates were going to change the amount of stiffness and make it change in stiffness relatively gradually as you approach the primary connection plate. So we cut up these little plates, brought the bridge to the weld shop. What could possibly go wrong? Well, when they added these plates, it pulled the primary plates back 3/32 of an inch. That doesn't sound like a lot, but that put 6 inches of camber in the main span of the bridge. Our secondary system wouldn't fit. We were sunk. So what did we do? We ended up reaming out each one of the holes to 12 millimeters. And this was all done by hand with a few days before the competition. And Sylvia, the night before, was out coloring all of our 12mm hardware with an orange Sharpie so our build team knew what hardware to put in the new holes. But we made it to the competition, and we're really happy with how we performed.
So as Jay said, we survived that disaster. But our bridge arrived on site in one piece. We're extremely confident going into the competition because all of the hard work that we put into practices. So this is a picture of the build team during competition, and once that cantilever section was in place, our nerves definitely calmed down, and we put together the quickest run and cleanest run that our team ever put together. So this is a picture of the vertical loading that Scotty touched about. We may not look too nervous, but seconds after, the instrument that measured deflection kept on spinning and spinning and spinning. Brian was there, so initially we felt that we failed the vertical loading, but we realized that there was actually a slip between one of the columns and the steel plates. So we were able to reload the bridge onto a much smoother surface and pass the vertical loading.
Yeah, the whole bridge was sinking into the asphalt.
So we were extremely proud of the competition results. It was a very competitive competition, but we achieved and exceeded each and every one of our design goals. So as far as construction speed, our design goal was to construct it in 20 minutes. We completed it in 14 minutes and 45 seconds. Our goal for weight was 200 pounds. It ended up being 165 pounds. As far as display, which the judges used based upon our poster board, which is outside in the quad, but it's pretty much similar to this handout that you have here, as well as the aesthetics proportion of our bridge. We're hoping to just be in the top 5, but we're very surprised when we found out we came in 3rd. It was pretty cool. We won this little paper award. For stiffness, our design goal was 1 inch, but it ended up deflecting only 698 thousandths of an inch. So the cost equations that Sky touched upon at the beginning of the presentation, it summed up into the overall performance of $8.5 million. And once again, this wasn't the cost of our bridge, but rather a way that the judges could use to compare the 11 other bridges in the competition.
Thank you, Ren. Just as important as our successes is to kind of reflect on our lessons learned. From just challenges of other years, we've realized that it was important to be proactive and very professional in reaching out to industry because we relied on industry to really be able to have a bridge that performs at the level of everyone else's competition. Also, we had issues with scheduling. None of us had done this project before. How do you schedule a project you've never put together? We try to be proactive in this also in having longer durations, and whenever something did exceed, we would reorganize the schedule to make sure we still had the same end date, because after all, the competition came around and you had to have a bridge. And then lastly, we didn't have the amount of training really needed going into this. Most of us had never welded before, and so in May we set out to be able to have welding on campus. It wasn't until March before we were able to have supervised welding for some of our testing. So, we encourage the School of Engineering and the Civil Engineering Department to move forward with this and be able to have it established for other years to come so they don't have to go through the process of getting this on campus. Some of our just bigger overall accomplishments, we were a very dedicated team. We built every weekend leading into the competition. Friday, Saturday, Sunday, we're in here for 5 to 8 hours, us 4, and also our build team. So our build team actually knew how our bridge came together and the struggles we had, getting everything to be very precise. We are proud to say we were funded by over 12 companies and interest groups, which really helped have that competitive bridge. And like I said, we are probably the most competitive bridge Santa Clara has put together for this competition. And that speaks of the goal we had originally, to be able to have a legacy here at Santa Clara that we can go to this competition and really, place in the top schools. We've moved that forward a mile, but we still, encourage and want continuity so that future years keep doing that little by little until hopefully we can qualify for nationals. And Scott, I see in the back, we look forward to being here next year and watching you present the 2014 team. So just before we conclude, special thanks to the build group, the juniors and sophomores that put in so much time for this bridge, and also our sponsors. Both you guys were really influential in having such a successful bridge. So thank you. We will now open for questions.
How did you guys analyze this then? What did you use?
A program called Visual Analysis, provided by the School of Civil Engineering, open to all students.
Yeah, and then for all the visual analysis stuff was verified by hand, so, and it was actually done completely independently. So we kind of had a general idea of what we wanted the bridge to look like and what each part of it needed to look like. And then, so while Scotty was in visual analysis, I was doing everything
So
by hand.
actually, to pull off on that, so the visual analysis program actually kind of shocked us when we went back to look at the results. So that aggregate deflection we talked about, it came out to be 0.698 inches, and in the program it came out to be 0.65 inches, something around there. And then the total weight of the bridge was around 165.
Essentially spot on.
Essentially spot on, 3-pound difference. So it was a very good program that we used. We were really happy with it.
If I understand it, on the cantilever part, would you put 1,000 pounds on?
Yes.
That's correct.
Now, then the compression was in your secondary, I mean the bottom.
Yes, that is why we designed a little bigger of a section. Yeah, so we did actually design for that we knew that it would create some tension in that secondary system.
And really, we weren't expecting that to be engaged all that much because the primary system is so stiff. So really, we were, where we had a lot of extra deflection in that main span, that's when that secondary system really gets engaged, when the bridge sags a tremendous amount.
Because it's such a long span, it's 13 feet compared to 3 feet, so.
So where was the 0.69 deflection total?
So
What
there's-
what
so
was
that-
in the main span and what was on the cantilever?
So,
You have a slide.
yeah, we have a slide at the end with our results. So,
I think it was 210 thousandths in the main span.
Yep.
And 268 thousandths on the
The
camera.
results slide.
yeah, so,
You can't see it.
pull that up.
Display slide.
So what the
So,
rule,
if you can see, so this BV, that's in the main span, and then these two values were on either side of the cantilever decking surface. So you can see a little variance. We don't really know what that was due to. Maybe an uneven surface, but
so for next year, for instance, will the design thing, it'll still be a bridge and you'll know the loads and it'll be a different span?
different span. So
And-
yeah, so they come out with the rules at the beginning of the fall. So last year they actually had a 23-foot long span bridge, so it was a little longer, so a little more weight.
And there's changes in rules to what the decking surface needs to look like.
Or what the connections can be.
Restrictions in connections. So last year, lock by twisting connections were allowed, and Berkeley had a connection that they just and stuck a bolt through it, and the bolt wasn't holding any load. This year they said, that doesn't, that's going to be penalized. So Davis had a really cool connection this year. It looked a lot like a dovetail, and my guess is that that'll be penalized next year, that kind of thing.
And just to add a little more, the rules actually say the options of where it would be loaded, but after all, it's the roll of the dice that really determines where the loading goes. So you have to design for your worst case.
Yeah, so the day before, they actually rolled the die, and we actually found out where they would be loading it. There were 2 different cases that we had to design for, so.
Yes, in the back?
Okay.
Yes,
How
in
did
the
you end up in the competition overall?
Good question.
We're right in the middle of the pack.
We placed 6th overall out of the 11 schools, and as far as all the categories that we showed, we were pretty much in the middle of the pack for each and every competition. We weren't in the bottom half at all, which we felt was a major achievement from Bridges in the past.
Yeah, we were competitive in every category.
Yeah.
So you guys did all the welding
Uh,
yourself?
I welded all of this myself, but I didn't trust myself to do the bridge. So the bridge was done by S&S in San Jose, and most of it was done with TIG. I've only learned how to do TIG.
Did all the other competitors in there have to do welding or?
Yes, and there's no rule against reaching out to industry support for that, so
Usually more than half will have it professionally welded. There are some schools that tend to have the smaller budgets that have to do the welding themselves. And that was one of the things that off the top, we didn't want to do the welding ourselves for that reason. We wanted a competitive bridge. So we reached out and got funding so that we could have it professionally welded. Jay did do some of the connection welding. So that was the welding we did back in March. So we had some experience, and we all were trained in welding as well early on.
And it was really our intention to weld it ourselves. We had a few difficult steps to pass by. We wanted to actually weld on campus. There were a few hurdles we had to get over. Kind of delayed our process, so we were kind of shoved into really using industry support to help us weld it. Otherwise,
But because of that, we had the most beautiful, we're not very,
beautiful bridge.
yeah, beautiful bridge, yeah, exactly, we had the best
But
welding.
you guys are welcome to come see in the quad.
Yeah,
It's out
in
in the
quad
quad
at this
afterwards.
point.
And just to note, we feel like we've really moved the competition forward, but we really want to keep seeing Santa Clara participate. They've kind of already wanted to just move on and not think about Steel Bridge for next year. We think it's important to start now for Steel Bridge, to push concrete canoe forward. We didn't have a canoe this year. In fact, all of us wanted to do concrete canoe, but we thought the process of developing a half-inch thick canoe with 3 different kinds of reinforcement was a more than a year-long process. So we really hope to see Santa Clara continue to do well.
Well, next year, is the team already decided they're gonna do a four-person crew?
We don't know. It's really up to, I guess, the School of Engineering or whoever wants to do it, and if they approve.
Yeah, we would encourage a bigger group.